Welcome! In this video, we will tackle LeetCode problem number 385, titled Mini Parser. This problem challenges us to parse a nested list structure represented as a string. It's a great opportunity to enhance our string parsing and recursion skills. Let's dive in and explore the solution step by step. In this problem, you are tasked with implementing a parser that takes a nested list of integers represented as a JSON-like string, S, and constructs a corresponding nested data structure. The string can contain integers or nested lists, where lists are enclosed in square brackets and elements are separated by commas. Your goal is to create a class called nestedInteger that provides methods to work with this structure. These methods include checking if the object holds a single integer, retrieving that integer, setting the object to hold an integer, adding another nested integer object to form a nested list, and finally retrieving the list itself. This ensures we have a clear and flexible interface for handling both integers and nested lists. The main task is to implement the deserialize function, which takes a string S and returns a nested integer object that represents the structure described by the input. For example, if the input string is 324, the function will return a nested integer object holding the integer value 324. This is a straightforward case because the input represents a single integer, so the nested integer object does not need to handle any nested lists in this scenario. In a more complex example, if the input string is 123, 456, 789, the deserialize function must construct a nested integer object that represents this nested hierarchy. The structure here consists of a top-level list containing the integer 123 and another nested list. That nested list holds the integer 456 and yet another nested list, which contains the integer 789. The nested integer object must accurately reflect this hierarchy by nesting the lists and integers within each other as described by the input string. Now consider the input string, which represents an empty list. In this case, the nested integer object should be initialized to hold an empty list. Additionally, there are some constraints to keep in mind. The input string is always guaranteed to be a valid JSON-like structure, and all integers within the string fall within the range of -10 to the power of 6 to 10 to the power of 6. The string could represent a single integer, an empty list, or a nested structure of varying complexity. These constraints help ensure that the input is well-formed and can be parsed without ambiguity. When handling edge cases, there are several scenarios to consider. For example, if the input is a single integer like 123, the output should be a nested integer object holding that integer. For an empty list, such as, the object should hold an empty nested list. A deeply nested structure like 1, 2, 3 must be parsed into a nested integer object that reflects the full depth and organization of the data. Additionally, the function must handle negative integers, such as -1, 2-3, ensuring that the nested list correctly includes the negative values. Lastly, if the input is a single negative integer like -456, the resulting nested integer object should simply hold that integer. These examples highlight the variety of cases the deserialize function must handle correctly. To tackle the mini parser problem, we need to parse a string that represents a nested list structure. This string can have integers, nested lists, or even empty lists, and our goal is to construct a nested integer object that captures this structure. The main challenges here involve correctly handling nested structures, distinguishing between integers and lists, and ensuring robustness against malformed or empty inputs. One approach to consider is the recursive method, which is a natural fit for this type of problem. Here's the intuition: nested structures can be treated as smaller subproblems. When we encounter an opening bracket, it signals the start of a new nested list, and we dive deeper. A closing bracket means we're done with the current list and return to the previous level. Digits are parsed as integers and added to the current list. To implement this approach, we use a helper function to process the string while maintaining an index pointer to track our position. This helper function recursively parses sublists and integers, building the nested integer object step by step as we traverse the string. The recursive approach has a clear complexity profile. The time complexity is O(n), where n is the length of the string, because we process each character exactly once. The space complexity is O(d), where d represents the maximum depth of nesting, as each recursive call adds to the call stack. However, recursion is not the only way to solve this problem. Another option is an iterative approach using a stack. This builds on the same intuition but avoids recursion by explicitly using a stack to manage nested structures. Here's how it works. When we encounter an opening bracket, we push a new nested integer onto the stack. A closing bracket signals the end of the current nested list, so we pop the top item from the stack and add it to the parent object below it. Integers encountered in between are added directly to the current top of the stack. The iterative stack-based method has the same time complexity, O, n, since each character is processed once. The space complexity is also O, d, where d is the maximum depth of nesting, as the stack mimics the depth of recursion. Another approach to solving this problem is to pre-process the string by splitting it into tokens using characters like and comma as delimiters and then manually parsing the integers and lists from these tokens. While this method might seem straightforward at first, it comes with significant drawbacks. First, splitting the string into tokens introduces additional pre-processing overhead, which can be inefficient. Second, this approach is prone to errors, especially when handling edge cases like empty lists or negative integers. These complexities make it less practical compared to the recursive or iterative stack-based solutions. In terms of complexity, the time required is O, n squared, as splitting the string and reparsing the tokens involves additional passes over the data. The space complexity is O, n, for storing the tokens. Overall, this approach is neither efficient nor reliable for this particular problem. Considering the alternatives, the chosen strategy is the iterative approach using a stack. This method is efficient, straightforward, and avoids the pitfalls of recursion, such as stack overflow when dealing with deeply nested inputs. The key insight here is that while the problem is inherently recursive, we can simulate recursion explicitly with a stack. This allows us to handle large inputs with controlled memory usage. There are trade-offs to consider. The recursive approach is elegant and easy to understand but risks stack overflow on deeply nested structures. On the other hand, the iterative stack-based method is slightly more verbose to implement but does not face the same memory limitations. The string splitting method, as discussed, is impractical due to its inefficiency and the complexity of handling edge cases. Ultimately, the stack-based approach strikes the right balance, offering robustness, efficiency, and clarity in implementation. It processes each character exactly once, ensuring optimal time complexity, and its memory requirements are predictable, scaling with the depth of nesting. Finally, let's summarize the complexity of the chosen approach. The time complexity is O, n, where n is the length of the string, as each character in the input is processed exactly once. The space complexity is O, d, where d represents the maximum depth of nesting in the input string. This accounts for the stack used to manage nested structures. Together, these complexity measures make the stack-based iterative approach both efficient and practical for solving the mini-parser problem, even when handling deeply nested or large inputs. The problem we are solving is LeetCode number 385, titled Mini-Parser. It requires us to parse a string representation of a nested list structure and construct a corresponding nested integer object. This string can represent three types of data: a single integer like 123, nested lists such as 123, 456, 789, or even empty lists denoted by. To tackle this, we'll rely on a few data structures. The primary one is a stack, which helps us manage the hierarchical nature of nested lists during parsing, with each element in the stack corresponding to a nested integer object under construction. Additionally, we'll use a temporary variable, referred to as the current number buffer, to accumulate digits for multi-digit integers. Finally, once the parsing is complete, the top-level nested integer object in the stack will represent the entire nested structure and serve as our final output. To approach this problem effectively, we need to understand a few key insights. First, nested lists have a naturally recursive structure. While recursion could work, we can simulate it iteratively using a stack, which is often more memory efficient. Next, we interpret opening brackets as the start of a new nested integer, while closing brackets signal the completion of the current nested integer. Lastly, when parsing integers, we accumulate digits into a buffer until we encounter a non-digit character, at which point we convert the buffer to an integer. With these insights, our algorithm begins by initializing three components: an empty stack for nested integer objects, the current _number buffer set to none to accumulate digits, and a negative flag initialized to false for handling negative numbers. Once initialized, we process each character in the input string one by one, evaluating its role in constructing the nested structure. When iterating through the input string, specific characters trigger specific actions. For an opening bracket, we create a new nested integer object and push it onto the stack, marking the start of a new nested list. Conversely, when we encounter a closing bracket, we first check if the current _number buffer is not none. If it contains a number, we convert it into a nested integer and add it to the top nested integer on the stack. Afterward, we pop the top nested integer from the stack, and if the stack still has elements, we add this popped object to the next nested integer in the stack. For digits between 0 and 9, we accumulate them in the current _number buffer, remembering to account for the negative flag if it was set earlier. If we encounter a negative sign, dash, we set the negative flag to true, preparing to handle an upcoming negative number. When processing commas, which separate elements in the nested structure, we first check whether the current _number buffer contains a valid number. If it does, we convert it into a nested integer object and add it to the top nested integer on the stack. Then, we reset both the current _number and the negative flag to prepare for parsing the next potential number. After processing all characters in the string, the algorithm finalizes the output. If the stack contains only one nested integer, it represents the entire parsed structure. This top-level nested integer is returned as the final result. In addition to this general flow, we also account for several edge cases, such as correctly parsing an empty list as an empty nested integer, handling single integers like 123 as standalone nested integer objects, accommodating deeply nested inputs like 123, 456, 789, and ensuring negative numbers such as -123 are parsed correctly. Now, let's analyze the time and space complexity of this algorithm. The time complexity is O(n), where n is the length of the input string. Each character in the string is processed exactly once, making this approach linear with respect to the input size. The space complexity is also O(n) in the worst case, which occurs when the input consists of deeply nested lists. In such cases, the stack holds multiple nested integer objects at the same time. To illustrate how the algorithm works, consider the example input, 123, 456, 789. First, we parse the opening bracket and push a new nested integer onto the stack. Then, we process 123 and add it to the top nested integer. Another triggers a new push, and 456 is added to the nested object. Similarly, initiates another nested integer for 789. Closing brackets progressively pop and merge nested integer objects until the structure, 123, 456, 789, is finalized. To optimize further, we minimize redundant integer conversions by delaying them until necessary and using lazy evaluation for number creation. Here, we're defining a class called nested integer, which will be the building block for our solution. The constructor __init__ initializes an instance. If no value is provided, it sets up an empty list to represent a nested structure. If a value is given, it assumes this instance represents a single integer. The isInteger method checks whether the instance holds a single integer or a nested list. The add method allows us to append elements to the nested list, ensuring that the internal structure is set to a list if it wasn't already. The setInteger method is used to assign a value to the instance as an integer, resetting any previous list structure. Finally, we have getInteger and getList methods to retrieve the current integer value or the list, respectively, depending on the instance's type. This class provides the foundation to handle both single integers and nested structures seamlessly. Now we move to the solution class, where we define the deserialize method to parse a string into a nested integer object. If the string doesn't start with a square bracket, it represents a single integer, so we directly return a nested integer instance with that value. For nested structures, we use a stack to manage multiple levels of nesting. We iterate through each character in the string. When encountering an opening bracket, we create a new nested integer object, pushing the current one to the stack if it exists. When a closing bracket is found, it signals the end of a nested structure. If there's a pending number, we convert it to a nested integer and add it to the current object. If the stack isn't empty, the top object from the stack becomes the parent of the current object. Commas indicate the separation of elements, so any pending number is added to the current nested integer. For numeric characters, we build the number incrementally. Finally, once the loop completes, we return the current nested integer object. This object represents the fully parsed structure, whether it's a single integer or a nested list. The deserialize method effectively handles all cases of input strings, constructing the appropriate nested integer representation as its output. Here, we begin with the nested integer class, which is the foundational structure for this problem. It can either hold a single integer or a list of other nested integer objects. We start by defining two private fields, value, which holds the integer if this object represents a single value, and list, which is a container for a nested list. The class has two constructors. The first initializes an empty list, which represents a nested structure with no values yet. The second constructor initializes the object to hold a single integer. To check the type of the current object, the isInteger method is provided. It returns true if the object holds a single integer, determined by whether value is not null. Finally, the getInteger method retrieves the integer value if this object represents a single integer, or returns null if it holds a list instead. This forms the basis of how we will handle and differentiate between integers and nested structures in our solution. The setInteger method is used to modify the object so that it holds a single integer. When this happens, the list field is set to null because the object can no longer represent a nested structure. On the other hand, the add method allows us to treat this object as a nested list by adding another nested integer object to it. If the list field hasn't been initialized yet, it is created as an empty list. Then, the provided nested integer is added to the list. To retrieve the nested structure, the getList method is used. This method returns the list if the object is a nested structure, or null if it holds a single integer. Following this, we move to the solution class, where the deserialize method is implemented to convert a string representation into a nested integer object. The first condition checks whether the string represents a single integer, identified by the absence of a leading character. If that's the case, we directly parse the integer and return it as a new nested integer object. When dealing with a string that represents a nested structure, a stack is used to manage the hierarchy as we parse the input. A nested integer object called current keeps track of the current level of nesting, while a string builder named number temporarily stores digits for numeric values. As we iterate through the characters of the string, encountering an opening bracket signals the start of a new nested structure. If there's already a current object, it's pushed onto the stack to preserve the context of the outer structure. A new nested integer is then created to represent the inner structure. A closing bracket indicates the end of a nested structure. If there are digits accumulated in number, they are parsed into a nested integer and added to the current object before resetting number. If the stack isn't empty, the top element is popped, and the current nested structure is added to it. The current variable is then updated to point back to the outer structure. Commas are used to separate values, so encountering one prompts us to finalize any number stored in number and add it to the current object. Finally, for any other character, such as a digit or a minus sign, we append it to number. After processing all characters in the string, the current object holds the fully constructed nested integer representation of the input. This is returned as the result of the deserialize method. The use of a stack ensures that the nested structures are built in the correct hierarchical order, while the string builder helps efficiently handle multi-digit numbers. This implementation effectively handles any valid input string, whether it represents a single integer or a deeply nested structure, and converts it into the desired format for further manipulation. To begin, we examine the simplest case, where the input string is just 324. Since the string does not start with an opening square bracket, we know it represents a single integer rather than a list. We check this condition with s0 equals, which evaluates to true. As a result, we directly initialize a nested integer object with the value 324. At this point, the state of the nested integer object is _value 324 _list none, meaning it holds the integer 324 and no list. Finally, the function returns this nested integer object as the result, encapsulating the integer value 324. Now let's move to a more complex example with the input string 123, 456, 789. First, we initialize essential variables, an empty stack, current set to none, and an empty string number for parsing numbers. As we parse the string character by character, we encounter the first, which indicates the start of a new list. A new nested integer object is created for this list, and current now refers to it. At this stage, the current object is in the state _value, none _list. Next, we see the characters 1, 2, and 3, which form the number 123. When we encounter the comma, it marks the end of this number. We then create a nested integer object for the number 123, add it to the current list, and reset number to an empty string. After resetting number, the state of current becomes _list 123 _value, none. Next, we encounter another, indicating the start of a nested list. At this point, we push the current object onto the stack, as it represents the parent list. We then create a new nested integer object to represent the nested list, and current is updated to point to this new object. The stack now holds one item _list 123 _value, none, while current is in the state _value, none _list. As we proceed, we parse the digits 4, 5, and 6, forming the number 456. When we reach the comma, it signals the end of this number. A new nested integer object is created for 456, added to current, and number is reset once more. The state of current at this point becomes _list 456 _value, none. Another, marking the start of another nested list, prompts us to push current onto the stack and initialize a new nested integer object for this deeper nested list. At this stage, the stack contains two items, _list 123 _value, none, and _list 456 _value, none. Meanwhile, current is set to a new nested integer object in the state _value, none _list. We then parse the digits 7, 8, and 9, building the number 789. Upon encountering the closing bracket, we know the nested list ends. A nested integer object is created for 789 and added to the current list. Next, we pop the top object from the stack, which represents the parent list, and add the current nested list to it. The state now reflects the stack containing _list 123 _value, none, and current holding _list 456 789 _value, none. Finally, another closing bracket indicates the end of the outer list. The current object is added to the top of the stack, resulting in the final state where current represents _list 123 456 789 _value, none. The function then returns this nested integer object representing the complete nested structure. In this example, the input string is, which represents a list containing an empty list. We begin by initializing the same variables as before, an empty stack, current set to none, and number as an empty string. As we parse the string, the first character is, signaling the start of a new list. A new nested integer object is created, and current is updated to this new object, which is initially empty with the state _list _value, none. When we encounter another, it marks the start of a nested list. To handle this, the current object is pushed onto the stack so it can be returned to later. A new nested integer object is then created for the nested list, and current now refers to this new object. The stack at this point contains one item _list _value, none, while current is in the state _list _value, none. Next, we encounter the closing bracket, which indicates the end of the inner list. The current object, representing the empty nested list, is added to the parent list stored in the stack. At this point, the stack is empty, and current reflects the state _list _value, none. Another closing bracket marks the end of the outer list and the completion of parsing. The function then returns the current object, which now encapsulates the entire structure as a nested integer object representing. The time complexity of the deserialize function is O(n), where n is the length of the input string s. This is because the function processes each character in the string exactly once using a single for loop. Within this loop, different operations are performed based on the character encountered. For instance, when encountering A, the function creates a new nested integer object and pushes the current object onto a stack. Both of these actions involve constant time operations, O1. Similarly, when A is encountered, the function pops an element from the stack and adds the current object to it, which also takes O1, as the add operation appends to a Python list. Characters like digits or commas are handled by either accumulating the number through string concatenation or converting it to an integer and adding it to the current object. These operations, such as string concatenation and integer conversion, are also constant time for reasonably small numbers. Since all characters in the input string are processed in this way, the overall time complexity of the function is O(n). Because the loop processes the input string s linearly, and all operations inside the loop take constant time, the total time complexity remains O(n). Now, turning to space complexity, the deserialize function requires O(n) space. One of the main contributors to this is the stack, which stores references to partially constructed nested integer objects during parsing. The size of the stack depends on the nesting depth of the input. For example, in the worst-case scenario, such as deeply nested structures like 1, the nesting depth k can approach n, leading to O(n) space usage for the stack. On the other hand, for shallowly nested or balanced inputs, the stack depth remains small, contributing less to the overall memory usage. Additionally, the function creates nested integer objects for each list or integer found in the input. Since the total number of these objects is proportional to the size of the input string, the memory required for storing these objects also scales linearly with n, contributing O(n) to the space complexity. Temporary variables, such as the number string, also contribute to space usage, but their impact is minimal compared to the overall size of the input. The number variable temporarily holds digits of an integer during parsing, and its size is proportional to the length of the largest integer in the input. However, this is negligible relative to the total size of the string s. When all factors are combined, the space complexity is dominated by the stack and the memory required for nested integer objects, resulting in an overall space complexity of O(n). To analyze the best, average, and worst cases, consider the following scenarios. In the best case, where the input is a single integer, such as 123, the time complexity remains O(n), because the string is still fully parsed. However, the space complexity is O(1), since no stack is needed, and only one nested integer object is created. In the average case, for a moderately nested structure like 123, 456,789, the function still processes all characters, maintaining O(n) time complexity. The space complexity in this case is O(n) as well, due to the stack and the nested integer objects created. In the worst case, where the input is deeply nested, such as 1, the time complexity remains O(n), since the function must iterate through all characters. However, the space complexity becomes O(n) due to the maximum stack depth and the creation of nested integer objects. Comparing this approach to a naive or brute force implementation highlights its efficiency. A naive method might involve recursively splitting the string and processing substrings. This would result in a time complexity of O(n squared, because slicing operations repeatedly create new substrings, and a space complexity of O(n squared, due to the memory overhead of storing these substrings. By contrast, the provided solution avoids slicing altogether, processing the string in a single pass and using a stack to handle nested structures efficiently. This results in both time and space complexities of O(n), making it a significant improvement over the naive approach and well suited for handling large inputs. When tackling this problem, there are several common mistakes to watch out for. First, incorrectly handling empty lists is a frequent issue. Some solutions mistakenly interpret as null or throw an error, but this is incorrect because the problem specifies that empty lists are valid inputs. In these cases, you should return an empty nested integer object. Another error is failing to differentiate between integers and nested lists. For example, not verifying whether a substring represents a standalone integer or a nested structure can lead to runtime errors. This is especially problematic when parsing multi-digit numbers or deeply nested lists. Lastly, if you're using recursion, forgetting to include a proper base case or mishandling single integers can cause infinite recursion or stack overflow errors. This tends to happen with deeply nested inputs, so always ensure your recursion has a clear stopping point. Now, let's look at two more critical mistakes. One is not validating the input format. Assuming the input string is always well-formed can lead to unexpected behavior. For example, edge cases like 1, 2, or missing brackets might break your solution. It's important to include checks to handle malformed input gracefully. Another frequent issue involves inefficient string operations. Repeatedly slicing strings or manipulating them in a loop can drastically increase the runtime complexity, potentially leading to O(n)² or worse. This becomes especially problematic when dealing with large inputs, so aim for solutions that minimize excessive string operations. To excel in interviews, there are a few key insights to keep in mind. Problems involving nested structures often test your ability to recognize patterns in parsing and recursion. Interviewers are looking to see if you can handle both recursive and iterative methods effectively. Edge case handling is another critical area. Be prepared for scenarios like single integers, empty lists, and deeply nested structures, as these are often the deciding factor between a correct solution and one that fails under specific constraints. Additionally, consider iterative approaches with stacks as an alternative to recursion. While recursion is intuitive, using stacks demonstrates your understanding of optimization and memory management. Lastly, be mindful of time complexity. Parsing strings should ideally run in O(n), so avoid inefficient operations like repeated slicing. If you're interested in related problems, LeetCode 394, 341, 844, and 726 all involve similar parsing or nested structure challenges, making them excellent practice. There are several alternative approaches to solving this problem, each with its own trade-offs. Recursive parsing is a popular choice, where each recursive call process is either a sublist or an integer. This approach is intuitive and straightforward to implement, but it risks stack overflow errors if the input is deeply nested. Another option is iterative parsing using a stack. Here, you push lists onto the stack and pop them off when you encounter a closing bracket. This method is more robust for handling large or deeply nested inputs, but it requires careful stack management, which can make it less intuitive. Finally, there's the two-pointer parsing approach, which uses two pointers to identify integers and nested substructures within the string. While this method can be efficient for simpler cases, it tends to become harder to maintain as the complexity of nested inputs increases. Each of these approaches has strengths and weaknesses, so choose the one that best suits the problem's constraints and your comfort level. Great job! We've successfully tackled the mini parser problem by breaking it down into manageable steps. Remember, recursion and edge case handling are crucial for problems like this. Thanks for watching, and don't forget to like, subscribe, and keep coding. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!